I met a geologist at a place where he said we could understand this better.
You see the quietness, the expanse, nothing to disturb you. Yet you've got the reminder that it was explosive in the past. There was this volcano back here, this cinder cone volcano, and it belched out this lava flow that spilled out across this countryside.
Just a huge amount of basalt, lava.
Yeah, but it's actually small compared to the lava flows that we see in many places. And there's something like 1,000 of these volcanoes around here. And the little one behind us here, we call that a cinder cone volcano.
You call that a little one?
Yeah, well, it is. I mean, these volcanoes are small. Mount St. Helens, 1980, when it erupted, okay? The top 2,500 feet of the volcano blew off, but that was small compared to historical eruptions. We can go back a little bit further to the Great Yellowstone eruption, and some of the volcanic ash was down in Texas. It blew that far away. You think about lava flows in India, that you have an accumulation of up to 1,000 feet over an area a third of the size of the subcontinent of India. What we see in the present is really only minuscule by comparison to what we've seen in the past. And that's telling us something about the historic past. We can't use present day rates of these processes to understand how quickly and how majestically, in terms of scale, the geological record accumulated.
Well, that is the point that has brought me to you, because how do we determine the age of these rocks?
Well, the important first thing is to recognise that this lava flow is, in a sense, an instant in time. It's an event. And when it's molten, you've got all the different elements that have come out of the volcano are all mixed up, and the rock starts to crystallise. Any of those atoms that are radioactive, they now start to accumulate what we call the daughter products, the decay products. Now, the point is that this rate of decay is so slow when we measure it in the present that, it takes millions of years for parent atoms to decay to daughter atoms. And so that's ultimately where the millions of years come from, the fact that the decay rates in the present are slow.
But we would say that the present is not really the key to the past, because obviously the past holds some massive, massive catastrophic events that are not going on today.
In fact, the Bible would say that the past is the key to the present. If you want to understand why the way the world is today, you've got to understand what happened in the past. So we've got lots of hints that geological processes haven't been at constant rates through time, and we have other hints that the decay rates may not have been constant. See, we've taken rock samples from a number of places, lots of samples in the Grand Canyon of each of these rock layers. I've done it in New Zealand. We've done it in other parts of the world. And what we've done is we've submitted the same samples to more than one of these dating methods. And so what we found is on the same samples with more than one method, we were getting ages that were different by hundreds of millions of years or even a billion years in some instances. We're seeing huge differences by using different methods.
Well, if there is that kind of a difference between all of these dating methods, then that would seem to confirm the fact that we have an open system here, not a closed one.
And if we have an open system, that means we can't trust it to give us dependable dates for these rocks. And that changes the whole thinking about the history of the Earth, because suddenly now these radioactive clocks are not reliable. We've got evidence that rates were faster in the past. Suddenly, we may not be thinking in terms of millions of years. We may be thinking in terms of a history that is much shorter.
But you were saying that this kind of evidence is in the open literature now.
Yes.
Why is it not making an impact?
Well, I've been asked that when I've spoken in university geology departments. And the answer is because there is a commitment to the millions of years. And so once people get locked into that focus, anything outside their field of view that conflicts with that focus is marginalised. And the reason why the millions of years are important, if we go back in the history of scientific thought, Charles Lyell in England proposed millions of years, and they multiplied the ages for the rocks. And that was the foundation on which Charles Darwin built. In fact, he read Charles Lyell's book and was convinced of the millions of years of geological evolution, so he could say, now, given enough time, what we don't see happening in the present. We might only see small changes in the present. Given millions of years, the small changes can add up to big changes. And so if you want to have a way of looking at the history that says that we got here by chance, random processes over millions of years, then you've got to have rocks that are millions of years old. Otherwise, you've undermined that whole foundation of that view of Earth history.
So time becomes the critical element for the conventional paradigm.
Exactly.
And that time has to be deep time.
Andrew said when you study the rock formations, they show evidence of a young Earth transformed by a global catastrophe. So he took me south to Sedona to see it for myself.
The important thing to note is that this landscape is actually very stable. There was lots of erosion in the past to carve out this whole terrain, but those cliffs and the valley floor are very stable, which is why you've got the vegetation. Today, everything's much, much quieter. Today's processes are extremely slow, but they can't explain how we got this erosion, how we got these layers, how we got these cliffs.
All right, so you wanted to come here because you see evidence of a young Earth because of what's here. What do you see?
Yes, well, the first thing we notice is the extent of these layers. It's like a stack of pancakes. For example, the red unit that goes all the way across our field of view, that's the Schnebly Hill Formation. And above that, you can see the first white unit is the Coconino Sandstone. And above that, you've got the Turaweep, and at the horizon, you've got the Kaibab Limestone, which is the rim rock of the Grand Canyon. And, you know, here we are, 70 more miles from the Grand Canyon, and these layers are still here.
Yeah. It's almost hard to imagine the volume of material that represents.
Yes, take the Coconino Sandstone. We can trace it from here, right across New Mexico, Colorado, right over towards Kansas and Oklahoma, or even in Texas. We're talking at least 200,000 square miles for this one rock unit that's consistent for mile after mile after mile. That's not the scale that we see today with localised sedimentation. And to get it flat lying like this over such a large area, it's like you have to make your pancake all at once very rapidly. And so these layers show evidence of rapid sedimentation, the extent of these layers.
Well, Andrew, you were talking about that red formation, but that doesn't sound familiar to me.
No, that's the Schnebly Hill Formation. It's not in the Grand Canyon. In the Grand Canyon, we go from the Coconino into the Hermit Formation. There's that knife edge boundary, and there's no evidence of erosion there, which means that the Hermit Formation was rapidly deposited, and then immediately the Coconino was a deposit on top of it. But here, we've come 70 miles from the Grand Canyon, and we've got this Schnebly Hill Formation between the Coconino and the Hermit. And this Schnebly Hill Formation, 800 to 1,000 feet thick, over an area of 1,000 square miles, had to have been formed very rapidly. If that took millions of years, we ought to see millions of years, evidence of millions of years erosion back in the Grand Canyon at that same boundary. We don't. So that means that this Schnebly Hill Formation in this area had to form in a matter of hours. So it tells you that not only is there a lack of erosion, but there's no time between those boundaries. So the whole sequence of layers was very rapidly deposited.
So we have this large extent of layers. We have the lack of erosion between the layers. What other evidence do you see?
Well, if we look closely, for example, at the Coconino Sandstone, we see the bedding, that there's bands within it that are sloping. We call those cross beds. What they indicate is that you had underwater sand waves were moving along. The comparison is in a desert. It's important to recognise that there's a difference in the angle in a desert dune. It's usually 30 to 34 degrees of these sloping beds. Underwater, it's usually 25 degrees or less. And Dr. John Whitmore has combed the hills around here with his students, hundreds and hundreds of measurements of these cross beds. And they all come in the range of 15 to 25 degrees. So it was underwater deposition. And so these layers are accumulating in hours, weeks, and within months, you've got this whole stack of pancake layers over such wide areas.
So it isn't a difference in believing in those layers that exist.
Not at all.
It's the difference of time, isn't it?
Correct. It's not a question of science versus the Bible. When we're talking about the flood paradigm and the conventional paradigm, we're actually talking about two different views of Earth history.
Those views really are different. Of course, I grew up being taught the conventional view with its long ages and slow, uniform changes. But what was the history of the world according to Genesis?